Mr. Richmond. This is your Integrated Math 2, Unit 13.5, Lesson Summary. Here in 13.5, we're going to actually return to factoring, which we first introduced in Unit 13.3. And we're going to take a look at a couple special products, special type of factoring methods that we can do when we have particular polynomials. So here are the four that we're going to take a look at that have some special cases for factoring. The first one is called the perfect square trinomial. And now, although there is a pattern to this, a shortcut to factoring these, it isn't actually kind of a required one, but it does speed things up. I still have the option of factoring this in the diamond method that I've shown in previous videos using 36 and 12. But all that happens is I get the same number, 6 and 6. And so that factor under the diamond method would become x plus 6 times x plus 6, which is equivalent to x plus 6 squared, because I have the same factor twice. But there's a shortcut here, and it's especially helpful, as you'll see when I get to problem B here, which can be a pretty nasty diamond problem to try to do. So let's talk about what the perfect square trinomial factoring method is. Here's what you're looking for to identify this. You need this first term to be a perfect square, x squared, so that's a perfect square. You need the last term to be a perfect square. 36 is a perfect square. You want to see what those become. So the square root of x squared is x. That's the square root of it. And actually, I'll show that. So let's go. The square root of x squared is x. The square root of 36 is 6. Okay? And what you need to have happen in order for this to be a perfect square trinomial is these two terms, x and 6, have to multiply together and be times by 2 to equal this. If that pattern exists, then you have a perfect square trinomial. And if you're able to recognize that fact that the square root of the first term, the square root of the last term, multiplied together and times by 2 equals the middle term, whether it's plus or minus, doesn't matter. It becomes a perfectly squared factor. And all you have to do is take those two terms, x and 6, write them together squared. And if it's plus, your sign is plus. If it's minus here, your sign is minus. And I'll show another one in example B here of how to use that in a moment. But for now, it's just a recognizable way to shortcut this factoring. However, a diamond will also suffice sometimes as well. So our next one is the difference of two squares. The big key here is not mixing up the difference. It has to be subtracting two perfect square terms. Just like this one had to start and end with a perfect square, and then we had that pattern in the middle. This one, we just need them to be perfect squares, but they must be being subtracted. Okay, similar method. I take the square root of 4x squared. I take the square root of 25, and as long as those are numbers I can actually work out easily and perfectly, then I can factor this way. So it's 2x and 5. So those become my terms. Here's just a memorization of patterns. What you want to do with those terms is do the terms added together as one of your binomials, and the terms subtracted from each other as your other. And that is our shortcut factoring method for the difference of two squares. Square root of the first term, square root of the last term, as long as they're being subtracted. You do plus and minus. And the reason it has to be plus and minus is you want the last two terms to multiply together. A plus and a minus make a negative, and that's how you get that negative second term. Now, fortunately, you can do this via a long diamond as well. However, it ends up taking up more time than knowing the pattern. I multiply the first and last numbers. 4 times negative 25 is negative 100. And this time there is no x term. There's nothing with x. So my top number is just 0. And so now it's just a matter of finding out what numbers multiply together to be negative 100. Well, that's 10 and negative 10, but add together to be 0. So it's the same idea as doing a trinomial diamond method, just you're missing the middle term, so you can make that middle term 0. And so this diamond method does work, but as you're going to see, it takes a significant amount more time. So I write x plus 10. And then because I had a 4 in the beginning, I have to divide by a 4 at the end. I have to simplify those fractions as much as possible. 10/4 simplifies to 5/2. And now that those are not factorable, I slide the denominator in front. And via the diamond method, I get the factoring. But again, as you can see, the great thing about the diamond method is it can be used in both these patterns here. However, it just does take longer. So it is in your best interest to try to memorize these patterns. Now, the next two are definitely a little bit more complicated. And you're definitely going to want the formula for this, the pattern with this, because there really is no easy way. So how do you factor the sum of two cubes or the difference of two cubes? Here you have two perfect cube items being added or two perfect cube items being subtracted. Notice for the cubes you can do both plus and minus. For squares you can only do minus. Okay, important note. So what's the pattern here? Well, this I just have to give you a formula for. The formula is to actually take the cube root of these and do a plus b times a squared minus the two terms multiplied together plus b squared. When it's subtraction, that formula changes slightly. It becomes a minus b times a squared plus ab plus b squared. Okay? And before I give you some clues on how to memorize this a little easier, let me talk about what a and b are. Well, a and b are the cube roots of these. So you take the cube root of x cubed, and that becomes your a. And you take the cube root of the second term, 8, and that becomes your b. So in the other one, same idea. I take the cube root of y cubed, I'm sorry, I forgot to put the root symbol on those. Cube root of y cubed equals your a, and the cube root of 27 on this one becomes your b. And so as long as they're perfect cubes and those can cube perfectly into a solid number, you're good to go. And you just write it into the pattern. So the cube root of x cubed is just x. So I'm going to replace all the a's in this with x. And that's the only ones that have an x. All the b's get replaced with the cube root of 8. Cube root of 8 means what number times itself 3 times equals 8? That's 2. 2 times 2 times 2 is 8. So all the b's get replaced with a 2. And then now once you've input all that, it's just a matter of cleaning it up. X plus 2 is as simplified as it's going to get. It's going to stay x plus 2. X squared is simplified. That's x squared. 2 times x, and a minus changes to minus 2x. And 2 squared is 4. And now I have this in my factor form. It should be x plus 2 times x squared minus 2x plus 4. Note here you do have a quadratic on the right. However, that is never factorable. If you do this correctly, that will never be factorable. You can try, you can do a diamond for it, 4 and negative 2. You will not find numbers that work though, okay? Just keep that in mind. This is the pattern, this is the equation. It always looks like this. It's a binomial times a quadratic to get these perfect cubes. Okay, let's now apply that to the second one. Y cubed minus 27. So the cube root of y cubed is just y. So my a is going to change to a y. My b is supposed to be the cube root of 27, which is 3. And then I can plug in a y squared. Okay, y times 3 is 3y, or y times 3. And then my last one is 3 squared. And again, I just clean it up. Y minus 3 times y squared plus 3y plus 9. Okay, now some important notes for this process and things that'll help you remember it. 1, these cube roots are just numbers. You'll notice I never use that sign at all. That plus sign, it just was what it was. I looked at just the x cubed and the 8. Didn't matter. Same with this. I ignored the negative sign. I just did cube root of 27, cube root of y. That's because the formula itself, the pattern itself, gives you the signs. The signs are always the same when it's plus, always the same when it's negative. How do you remember them? You remember SOAP. SOAP is your way to remember this. Okay? The signs are always going to go same, opposite, always positive. So when you write this, it's kind of easy to remember this portion. It's a and b, then a squared, a times a and b squared. If you just kind of say that over and over, you'll get that. A and b, then a squared, a times b squared. A and b, a squared, a times b squared. That's always the same in both these. And then remember the signs was so. Same sign as the original problem. And then opposite sign, so opposite of plus is minus. And then the last sign's always positive. Here, sign's minus, so same, minus. Opposite, positive, and then always positive. Now, should remember the pattern. So with that said, let's apply it to some problems now where the factoring isn't going to be clearly stated which of these to use. We have to recognize it. Now, before we move on too far, let's summarize all we've learned with factoring, because basically at this point now we can do all of our factoring. What are our methods? One, we still always factor by GCF first, if possible. If not possible, then step 2 is to identify what you have. Okay, if you have 2 terms left, the only thing you're going to be able to do potentially is this new one, the difference of squares. If you've taken out a GCF, that might be the only thing left for you to possibly do. If there's nothing like that to do, then you're done. If what you're left with has 3 terms, oh, no, I take that back. If it has 2 terms, you could do difference of squares, but you could also possibly have one of the cube ones. That's really the only 2 options you have if it has 2 terms. If it has 3 terms, we're going to do our diamond factoring. We could potentially do our long diamond factoring, although I would argue those are the same steps. Or you could potentially have a perfect square trinomial. Okay, and so that's our ordering for factoring. You're always going to try GCF first, and then based on the number of terms, you're going to try one of these methods. If there's 2 terms left after the GCF, try difference of squares or the sum or difference of cubes. If there's 3 terms left, do your diamond factoring or a perfect square trinomial. And if there's 4 terms left, well, that you learn in Math 3. Okay, we're going to do a little method called grouping, but we'll save that for next term or next year. So let's get started. We want to factor 18x squared minus 50. I always start with GCF. What goes into 18 and 50? Well, 2 does at least. I take a 2 out, I factor by the GCF, divide both those by 2. Here's what I'm left with, 2 times 9x squared minus 25. I'm stuck left with 2 terms, so I got to see if I can do one of these factoring methods, either difference of squares or sum or difference of cubes. I see that it is squares, and it is subtracting, so this is potentially factorable by the difference of cubes. So I'm going to check, what's the square root of 9x squared? What's the square root of 25? If it's possible to do those, I can write that factored in a shortcut. Square root of 9x squared is 3x, square root of 25 is 5. So this factors to 3x plus 5, 3x minus 5, and I just carry that GCF 2 on down. On to our second problem, which I had copied down wrong originally. It says, I believe 12x, it should say minus 24x, so make sure you fix that if you're writing ahead. Let's try factoring this. It is a trinomial. There's no GCF. 3 goes into 9, 24, but not 16. 4 goes into 24 and 16, but not 9. So I'm stuck doing a diamond for this, and it's not a nice one. 9 times 10 is 90. 9 times 6 is 54. 90 and 54 is 144. So I'm trying to find numbers that multiply to 144 and add a negative 24, and that is not necessarily easy. It's going to take me a little while. So no problem, I could do that. But when this happens to you, if the numbers are this big, take a second and pause and see if it might not be a perfect square trinomial, because it'll speed up the process potentially. So let's take the square root of these. What is the square root of 9x squared? Well, that's 3x. What's the square root of 16? That's 4. And our rule for a perfect square trinomial is that those squares, if the first and last number squared evenly and multiplied together, would be 12x, and doubled equal the middle term, you can do the perfect square trinomial factoring, which in this case it works. So I can actually just write this as the square roots of these, 3x. Since my middle sign's minus, I can do 3x minus 4, and this is the same as doing 3x minus 4 squared. Speeds it up. Now, here I have 8a cubed minus 27. I want to look for a GCF first. That's always step one. I don't see one, so I can move to step two, which is to factor either by difference of squares, sum of cubes, or difference of cubes. And this has a cube, so I'm going to go cube and minus means difference of cubes. And I'm going to start by finding what the cube roots of these are. The cube root of 8a cubed is 2a. The cube root of 27 is 3. So those are my a and b's in the formula. And I can just plug them right into my formula, which goes a, and remember SOAP, same, so minus b times a squared, SOAP again, same, opposite, and then a times b plus, always positive at the end, so plus b squared. Now I can plug them right in. 2a minus 3, and here's where it can be tricky. It's 2a squared, which means 2a times 2a. That actually changes to a 4a squared. 2a times 3 is 6a, and 3 squared is 9. Just a matter of plugging those in and working it out. And I now have it factored, and remember that second part, that quadratic part, is never factorable when doing this pattern. Okay, D, again, don't get excited because you see a cube, look for a GCF. 5 actually goes into both those, and it becomes x cubed plus 8. Oops, I wrote x squared, x cubed plus 8. And now I just have to factor x cubed plus 8 using my pattern. And my pattern, again, goes a plus b, a squared, opposite sign, ab, always positive, b squared. And now I just have to plug in the right terms for a and b. A is the cube root of the first term. The cube root of x cubed is x. Cube root of 8 is 2. So those are my a and b terms. And now it's just a matter of rewriting it with the right terms. So x plus 2 times x squared minus a times b is 2 times x, so 2x, plus 2 squared is 4. And I now have that written in completely factored form. Now, with that said, we can go back to what we did in the previous lesson, lesson 13.4, which was solving equations like this and finding roots of functions like this by setting it equal to 0 and factoring. Just now, our factoring can involve these new methods. So, let's take a look at the first problem. This one's already set equal to 0. You want to solve it, you just factor. Always factor by GCF first. 6 goes into all those. 6 times x squared plus 4x plus 4 equals 0. And x squared plus 4x plus 4 is a quadratic trinomial, which can be factored via the diamond, or potentially could be a perfect square trinomial. In this particular one, the square root of x squared is x, the square root of 4 is 2, 2 times x is 2x, doubled is 4x, that's a perfect square trinomial. So I can speed that up and just write that as x plus 2 squared. So I have 6 times x plus 2 squared. And at this point, you can still do the zero product property for these to solve, or you can treat it kind of like you would treat an equation and just try to isolate x. I could divide by 6 to both sides. Okay, 6, this divided by 6 crosses out the 6. 0 divided by 6 is 0. It doesn't change that side at all. Then I could square root both sides. Square root both sides. X plus 2 would be all I'm left with because the square root undoes a square. Square root of 0 is 0. Then I can subtract 2 from both sides and get that my answer for x must be -2. Okay? And this is actually what we're going to kind of get to in our next lesson, I believe, is how to solve this way. Another way to think of that one is it's basically a diamond with 4 and 4. So it's 2 and 2. So your factors are the same idea as x plus 2, x plus 2. So if you were to solve those, you get the same answer. The answer is just -2 twice. You don't need the same answer twice. Rewrite it once. Okay? B, when it's not given to you as an equation, but they want you to find roots, you have to know that those occur when the y portion of it is 0, or the function portion of it is 0. So I'm going to set it equal to 0 first, and then factor. Okay, what goes into 8 and 50? 4 goes into 8, 4 goes into 50. I think that's the GCF. I'm going to try that and see. Wait, 4 does not go into 50 perfectly. Don't know what I was thinking there. Let's try again. How about 2? 2 goes into 8 4 times. 2 goes into 50 25 times. That definitely looks a lot better, doesn't it? So 2 times 4x squared minus 25, that distributes out. I've factored out the GCF, and I have a difference of cubes, squared terms being subtracted. So I can use my difference of cube factoring. 4x squared factors at 2x plus 5 and 2x minus 5. Now how do you solve from here? Here's the thing, you still are doing the zero product property. There's just, the 2 doesn't have a variable at all. So you can pretty much ignore it. Or you can divide it out. Divide the whole side by 2 and this whole side by 2. 0 divided by 2 is 0. It really doesn't matter at all. I just have to find what values of x make 2x plus 5 equals 0 and 2x minus 5 equals 0. So I'm a little bit out of room, so we'll work it out here. We got to kind of work it out in our head and remember. I think we can all handle that. We're big boys and girls. Subtract 5 over. You get 2x equals negative 5. Divide by 2. You get x equals negative 5 over 2. On the other one, you add 5 over, you get positive 5. You divide by 2, you get x equals positive 5 over 2. So we actually end up with some fractional answers here. X equals negative 5 halves and x equals positive 5 halves. So this is really just a combination of the lessons you did in 13.3 and 13.4, factoring and solving via factoring, but we're using our slightly more difficult special products. Take the time to memorize the difference of squares, the sum and difference of cubes especially, because those are really difficult to do without the pattern. You get the pattern down, you get the factoring down, you get the problem right, everybody wins. Thank you.